The sound on this probably won't be too good because I forgot my microphone. I think it's laying on my desk in school. But you could probably still hear it if you even want to go through and look at it. All right, so what we're doing now is we're talking about a thing called polar coordinates. Did you watch the video on this?
Yeah.
Okay, so was it? It was like 2 sets, wasn't it, or 2 sections? Were they really? So I quit watching them now. I got tired of listening to him, so I open the book and I just teach myself through the book. So yeah, I mean he seems like a real nice guy, but it just need a little more energy from him, you know what I mean? Anyway. Yeah. Alright, so we're going to talk about polar coordinates. We've kind of already done this. This is probably real familiar to you anyway. Remember when you took a vector and you broke it down into component forms? Remember that? You had an x and a y. And, well, the vector itself was kind of like polar coordinates, to tell you the truth. So, remember we had magnitude and direction with vectors? That's basically what polar form is. It's just writing a point instead of, we call this the coordinate plane, right? And so we would just call this, I think they just call it a coordinate. Yeah, I think that's what they're going to call it, just a coordinate. But we can get to this point a couple different ways. We could start at the origin, right? Or they call that the pole. Remember him saying the pole? So you could start right here. We'll just say at the origin, right? You're used to that. How could you get to that point? Well, you could go in the x direction, right? This way, and then you can go up in the y direction, right? To get to that point. And then you would show it by an ordered pair, right? You're used to that. You did that back in pre-algebra, algebra 1, whenever you did that kind of stuff, okay? But there's another way to do it, and that's kind of like the vector stuff. So instead of going over to the right and then up, you know, up and down, excuse me, on the y-axis, what we're gonna do, we can go straight to it. Like if I was in New York City, right, and I wanted to go, if I wanted to start here and I wanted to get to this point over here, right, here's a pizza place, here I am, I want to get to pizza place. In New York City, you probably wouldn't go a direct route over, would you? Unless it's on the same street. What would you have to do? You go east, right, several blocks, and then you go north several blocks and you can get to it. But let's say you're out in the middle of a field, right, and you want to get to the cow. I don't know. I figured cows in the middle of the field, right? So you start right here, and what do? You're not going to go over and up, are you? You can go straight to that cow, couldn't you? You can go from here, and you can go directly, right from your starting point, right to where you wanted to end up. Does that make sense? All right, that's a vector. So if I told somebody, if you're sitting there, Jacob, you had to tell Emily, all right, there's the cow. I blindfolded you, and you got to go to the cow. I don't know. I'm just making these dumb illustrations up off the top of my head, okay? So, blindfolded, and you got to go pin the tail on a cow or something, right? Or the donkey. My uncle in West Virginia's got donkeys instead of cows. Isn't that crazy? Do you really? He's got about 20 full-size donkeys. But he lives on a farm and stuff, and he doesn't even do anything with them. I thought he said he would probably like maybe sell them or whatever, you know. But he got so attached to them, he keeps them as pets, and it's like a full-time job. Oh, I probably got at least 20 donkeys. Oh, it's amazing. I mean, he feeds them and everything else anyway. So there's my uncle's. His name is Nelson. Uncle Nelson. His donkey's right here. Okay. And whenever we get like Christmas cards and stuff, he always writes a poem and he incorporates the donkeys in it somehow. He lives by himself, you know? So up in the hills of West Virginia. So anyway, he starts right here. And if you go there, if Jacob, you had to tell Emily, you would probably say, all right, I want you to go 30 degrees, you know, you're facing this way. I want you to go 30 degrees, and I want you to take like 10 paces or something like that, right, to get to that spot. Or you could say, go to the right this many paces, and then go up, you know, go north this many paces. There's 2 ways to get to it. This would be the most direct way. This is the polar way of getting from one point to another. It's a magnitude, right, how much, and it's a direction, okay, of course, which direction. Does that make sense? It's all vectors. It's all this is. It's polar coordinates are basically the same thing that we've always done with vectors. You're going to use this a lot, again, when you take physics. This whole vector thing is really big in physics. So I don't know if you're going to take, you say you're graduating soon, right? So you probably won't even take a physics class, will you?
Probably
in college, right? Okay. Do they even have a physics? Do they offer physics here?
Mine's not
But
this year.
right, but anyway, if you ever take it, right, you'll look back on this and you're like, oh yeah, I remember all that vector stuff. We had a whole chapter on it. And the polar coordinates, that's going to be really super important, okay, when you take physics. It's going to deal with a lot of things. It's going to deal with velocities, it's going to deal with forces, accelerations, all kinds of stuff like that. So it's kind of a big deal. So that would be the polar form. How do we show it in polar form? It kind of looks like an ordered pair. You put the magnitude first, okay, you put a comma, and then you put the direction second. Now you don't just put a 30, put a degrees, and that is really the only indication that this is polar form and not regular rectangular form. Because if I just put 1030, you'd think you would go over 10 to the right and 30 up, wouldn't you? If it just said 10 comma 30. But with the degrees, that means this is polar form. Right? But what we want to do is they're going to ask you a couple times to change it from polar form to rectangular form, and then the other way around. They'll give you something in rectangular form, and then they want to change it to polar form. Right? So what if we wanted to change this to rectangular form? Well, what we'd have to do is figure out how far over to the right and how far up. There we go. All right. So we want to find out how far on the x direction and how far on the y direction. That would be our polar coordinate, wouldn't it? Because that would be xy right here. So how do we figure this out? How do we do x? You could go through sine, cosine, but he even comes up with a little formula. I think he says it's r, like cosine of theta. Do you remember him putting that on there? R means the resultant vector, okay, this magnitude right here. But we talked about this last week. We said if you want to solve for x, you could go through that whole sine cosine thing, but after a while you get used to it and it's really consistent. So x is going to equal, do you remember this? The hypotenuse times the what? Which trig function for the x? What do you think? The x direction. Come on, we've been doing this a lot. If you go in the x direction, we even wrote it as an ordered pair, right? Instead of saying xy, I could write that as an ordered pair. Which trig function goes along with the x? Remember? Remember alphabetical order? So x comes before y, something comes before something else. Cosine, very good. Cosine and then what? The sine, alright? That's really important, okay? That's really important right here, that you understand that the x goes with the cosine and the y and the sine go together. So what would this be? It would be the hypotenuse times the what? Looking in the x direction, which trig function do we use that goes in the x direction? The cosine, right? Okay. So if I wanted to solve for x, it would be 10 times the cosine of the angle. In this case, the angle is 30 degrees. Right? Whatever that number is. Cosine of 30 is the square root of 3 over 2. Let's just put that in our calculator. So, oops, look at that. Look what I've been doing. You can tell I've been working on that thing that they were doing later. What do we got? 10 cosine of 30. Oh, I don't know if I'm in degrees or not. Let's see. Oh, I'm all messed up. Let's change this to degrees. And let's change this to that. There we go. Alright, now let's see if it works. Boom. Yep. So it's about 8.7. Right? I'm not just making numbers up. It's not any examples or anything. So that'd be 8.7. Let's say it's meters. Okay, we'll just pretend. So you go over 8.7 meters, and how far up do you go? You can actually do this one without calculating. This would be 10 times the sine of 30. Get used to that, because you're going to be doing that a lot, okay? Now, you could have sat here and said, all right, I want to solve for x. This is adjacent. That's hypotenuse. The cosine of 30 is adjacent over hypotenuse, and then you solve for x. You could do that if you wanted to, but that's too much hassle, isn't it? After a while, you're going to figure out that it's always going to be this. It's always going to be the hypotenuse times the cosine of the angle. X will always be the hypotenuse times the cosine of the angle. The y, the up and down one, will always be the hypotenuse times the sine of the angle. Okay? Can you remember that for next time? So next time we say that, you'll just jump right on it, right? Okay. Let's do this one. Do you remember what the sine of 30 is? Remember, this is the short side, this is the long side. The long side was the square root of 3 over 2, right? What's the short side on a 30, 60, 90 triangle? 1/2, right? So just in your head, you should be able to figure that out. So it's 10 times a half, or a half of 10, which is 5. If you don't believe me, and I'm sure that you believe me, right? We go 10 sine of 30, and let's see what that is. It's 5, just like I said. I'm right once in a while. Not too often, but sometimes I am. Alright, so there you go. And that would be the coordinates. That's how you get to that point. You go 8.7 in the x direction, and you go 5 in the y direction. Do you understand what we're doing? You can get to this point 2 different ways. You could be in New York City, right? And go east 8.7 blocks, right? Probably be in the middle of a building somewhere. And then you go north 5, right? Or we could say 8.7 miles or whatever. So you go 8.7 over and you go 5 up. That gets you the same point as going 30 degrees 10 meters. Okay, so if I walk 10 meters at 30 degrees, I would get to the same exact point. You get there by 2 different ways. One way is by polar coordinates, and the other way is by rectangular. We call this rectangular coordinates. Okay? And what you're going to be doing is you're going to be switching back and forth from one to the other. And really, that's not much different than vectors, is it? It's really the same thing. It's the same thing. Polar form basically is vectors. It's using vectors. That's why they did this after they had that whole lesson on vectors. Okay? Make sense? You could, now they go through this thing right here. With polar form, you could say, and we've talked about this before, you could have started from the positive x-axis and just gone 30 degrees. Or you could have, you could have done this. Couldn't you? Remember that? You could have walked around the circle. Why would you want to do that? I don't know. But you could go all the way around the circle once and then go up 30 degrees. You'd be at the same spot, wouldn't you? You could keep doing that all day, couldn't you? Go around in circles, all right? You could have gone around a 360 and a 360 plus the 30, right? So the first time around the circle would be what? 360 plus 30 is what? 390. Or you could have gone 2 times around the circle plus the 30, which would be what's 2 times around the circle? 720, right? Plus the 30 is what? 750. So right here, you could have put, instead of 30, you could have put 390. That would get you at the same exact spot, wouldn't it? Or you could put, what did I say, 750? 750 would be at the same exact spot. I could keep adding 360 all day long if I wanted to, couldn't I? Right? And I'm still at that same exact spot. So with polar form, there's several different ways to write it. Here's another way to write it, which is a little different. Sometimes they can make that magnitude, negative. Let's do this in the same quadrant, or the same x and y axis. I'm going to tell you what, let's get rid of some stuff that we don't really need. We'll keep all that there. Change this to another color. Okay. We actually, tell you what I'll do. Watch this. I just want to copy and paste it. So it's the same exact angle. Right, now we'll change the color of it. There we go. Alright, now it looks nice and pretty. Now, I copied and pasted it, didn't I? So tell me something about the length of this red one compared to the orange one. It's 10, isn't it? Okay. Tell me something about the angle that it's making with the x-axis. It's 30. It's still the same exact thing, right? I copied and pasted it. So it's the same direction, and it's the same magnitude. You got that? Okay. But if I wanted to talk about this vector right here, this, actually, let's not even use this 30 right here. What if I wanted to keep that 30 right here? We actually say this. We say this is going in the opposite direction as this one. So we can actually put a negative 10. So this point right here, I could write it like this. I could say, tell you what, let me take a quick peek here. I just want to make sure. Hold on a second. Okay, this is what I was thinking. I think I was right. If I wanted to find this point right here, we can actually name this by its polar coordinates. We could write negative 10, right? And then watch this. I'm going to put 30 degrees here. What does this mean? This point right here, if I put, plot the point negative 10 comma 30 degrees, what you do is you go 30 degrees first, and then you draw, right, the 10, but that wouldn't be negative 10, would it? What's negative 10? Negative 10 means it's going in the complete opposite direction. So I took this, and it's completely the opposite direction, going 180 degrees, isn't it? From this direction. Do you follow me on that? So this point right here would actually be negative 10, 30. Even though you're like, well, wait a minute, this is like 180 plus 30. That's actually 210, isn't it? But you could write it like this. There's two different ways to write this point. See this point right here? You could have written it positive 10, 210 degrees. You see that? So that looks kind of weird. I don't know what the benefit, to tell you the truth, of writing negative 10, 30 degrees. It's just saying, okay, it's the magnitude is 10 at 30 degrees, but I'm just taking this and I'm taking it and I'm flipping it. It's like this. Watch. I think I can do this. Watch this. This would be cool. I guess I don't know how cool it is, but watch. I'll take this thing. It's going regular positive 10, right, at 30 degrees. Or I can take it and do this. And now it's going what? It's going in the complete opposite direction now, isn't it? 180 degrees. So now it's going negative 10 at 30 degrees. Okay? You see that? So it was here. Now it's going here. It's going the opposite direction, still at that 30 degrees. It was 30 degrees here. It's just going in the opposite direction, so it's negative 10, 30. Or I could just say it's positive 10. And then if I call it positive 10, I got to figure out what this angle is right there. And what's that angle? Remember, that little one in there is still 30, isn't it? So what did I do? I went 180 plus a little bit more, so that's 210. So these two right here put you at the same exact spot. So that gets a little weird when they put the negatives on there. Right? But that's what it means. Does that make any sense at all? Okay. All right. Let's do this. We kind of talked about this already, but let's do one that they do in the book. Okay, we're going to change from polar to rectangular, and then we're going to change from rectangular to polar. All right, so here we have two different ordered pair, or two different coordinate systems here. This is in polar form, and I want to change this to rectangular form. This one is in rectangular. I want to change it to polar. So what are we going to do? Let's draw the thing out. So 4 at 60 degrees. So I kind of like to make it kind of look like 60 degrees. Doesn't have to be exactly, but there's 60 degrees right there. So that is 60 degrees, and the length of that line is 4. And I have to just find, put it in rectangular form, which is basically just finding the components of that vector, right? So again, we did this all last week. So we're going to go like this, okay? And so what do I have? I've got an X and I got a Y. Now, to make it super easy, how do we do this? X is equal to what? How do I write that down? We just did it. Well, so before the hypotenuse, which is 4, times cosine of that angle. What's that angle? 60 degrees. Good. Let's do the Y while we're at it. Okay, so Y is what? 4 times the sine of the angle. See how easy that is? You just have to remember the cosine goes with the X and the sine goes with the Y. Alphabetical order. It's kind of easy to remember. Cosine of 60 is actually a half, isn't it? Right? Because that's the short side. Remember that? And so it's half of 4, which is what? 2. The sine of 60 is the square root of 3 over 2. That's something we'll put in the calculator. They don't want exact numbers. They want, decimal numbers on this. So I'll just hit 4 sine 60. And there we go. We'll go 2 places. 3.46. 3.46. So that's basically my coordinate, or my rectangular coordinates. But I write it as an ordered pair. What do I write? 2, 3.46. Now this was a pretty easy one because it was in the first quadrant. Okay. What if it was in the second one? What would the cosine be? What would the sine, S-I-G-N, all right, positive, negative? What would the sine of the cosine be? He's using sine twice, right? Because what's the sine of the sine, right? But two different words. Anyway, is it positive or negative? Is the cosine? That's easy. Is the cosine positive or negative in the second quadrant? It's negative. What's the sine? S-I-N-E. Positive. In the third quadrant, what's the cosine? Negative. What's the sine? Negative. What's the fourth quadrant? Cosine is positive and the sine is negative. Good. You got it. Okay? So we do the math, but then you look to see what quadrant it's in. You stick the appropriate signs in front of it, positive and negative, and then you're good to go. You understand what we're finding here? That's that point. I went over 2 and I went up 3.46. Boom. I'm at the same spot. as if I went 4 at 60 degrees. Okay? So I'm just changing from polar form to rectangular form. What about this one? Kind of the same thing. It's just we're kind of going backwards, right? We don't start off with the vector. We start off with the components, and we got to figure out what the vector is. So it's negative 3, 1. So I go negative 3, 1 right there. Then we'll make our little polar form thingy here. And then I can make a triangle out of that, can't I? Let's see. Colors. So I'm going to put a line right here, line right here. This time, what do I know though? I don't know the length and the angle. I know how far over I went, right? In the x direction, I know how far up I went. How far over to the left did I go? 3, right? And I can just put a 3 there, or you can put negative 3. It doesn't make any difference. How far up did you go? I went up 1. Okay. So how do I find the magnitude this time? Got a nice little right triangle. It's a big hint for you. How do I find that magnitude if it's a right triangle? Pythagorean theorem. Exactly right. Did you see that, Jacob? Did you see it? Okay, because it's a right triangle. I know 2 sides, and I can always find the third side. So I'm trying to find the length, aren't I? I'm trying to find that yellow line right there. How do I find the length of it? Pythagorean theorem. So a lot of times we'll call it R for resultant vector. Okay, so I'll call it R. So let's go back to yellow. I'm writing these things out. So what is it? It's going to be R squared equals 1 squared plus 3 squared. Do you really need the negative though here? I mean, you could put a negative in here and put that in parentheses, but that's kind of a waste because it's going to come out positive. Yeah, it's going to go away anyway, right? It's going to, because you square a negative, it's going to be positive. So I don't even bother doing that. All right. So what do we get? That's 1, that's 9, that's 10. So R equals the square root of 10, or let's find out what that is in the calculator. Square root of 10, and that is 3.16. 3.16. All right, that's our magnitude. That's how far it is right there. Oh, speaking of 3.1 something, you know today's Pi Day. Okay. Unfortunately, I'm not that good of a teacher. The other math teacher at Red Lion, she put on Facebook the other day, or last night, she got how many? Like 16 pies or something like that. She's bringing in 16 pies, and she's letting all her kids eat pie today for Pi Day. It's like, man, I wish I was that nice. I don't even think about it. But
on the way here, it's just like on the radio, it's Pi Day.
We'll be 3.14, and then it's at 1:59 because it's 3.14159. So at 1:59, 1 minute before 2 o'clock, today is Pi Day. So we'll be.
I'm really gonna have a big party.
I don't get that excited about it, but somebody. I even got another. I got another Facebook from a teacher who used to be at Red Lion, and she told me and the other math teacher who is the big pie person, right? Happy Pi Day. Anyway, I'm a pretty big dork, you know, math dork, but I'm not quite that big. So anyway,
why would I think of pie? I just think of numbers.
Yeah,
it's just about it.
Think of circles.
I don't need to celebrate. I don't need to
celebrate circles. All right. Anyway, whatever. All right. What do we got here? We're trying to find the angle now, aren't we? So we got to find that little angle right there. So how do we do that? And again, it's been pretty consistent. We've been doing this quite a bit. We did this a lot with vectors, and we're just doing it again with this polar form. So what trig function are we going to use? You could use any of them. Since you already found R, you actually know all 3 sides. You can use sine, cosine, or tangent. But let's just use the original numbers they gave us and forget the R. It's an approximation anyway, isn't it? So let's use the exact number. So what trig function? Boom, boom. Tangent, very good. Okay, remember using tangent on these? Right? The tangent is equal to opposite over adjacent, so it's 1 over 3. And then we solve for the theta, so it's the inverse tangent of 1 over 3. And then we put it in here so we can see it. So it's the second function tangent, 1 divided by 3. And it's about 18.43. Oh, there's the go. 18.43. Alright, and that's basically our answer. But how do we write our answer? Let's just write it up here. We write 3.16, put parentheses, and then you put your degrees. This is your degrees right here. Actually, I'm sorry, I lied to you, didn't I? It's not 18.43. I almost did that. That's this angle right here, but how do we show the angle? We have to show it from where? From the positive, well, yeah, from the positive x-axis, right? Over to here like this. Whoa, I almost put 18.43 in there. So this is the angle. You got to have a starting point. Your starting point is always the positive x-axis on this. We have to go counterclockwise. So what's this big angle right here going to be? Well, I know this is 18. Yeah, you got it. It's 180. Yeah, let's put it right here. It's 180 minus 18.43. Okay? And that would be, I wrote it down already, it's 161.57. And that is the angle that you want. Okay? 161.57 degrees. That's your polar form. Did you watch on there where he did this on the calculator? Change it from polar to rectangular? Almost hate to show you this, because you're going to say, why don't we just always do it on the calculator? Well, because, I'm glad you asked that question. Very good question. The reason he asked, the reason that we want to do it this way, because there's going to be problems on here that says, I want you to do this without using the rectangular and polar form on the calculator. Alright? So that's a reason. Alright? You want me to show you how to do it? Did he do this? I mean, it's in the book, but I don't know if he actually did it on the video or not. I can't remember.
Yeah, I kind of almost fell asleep on that.
Oh, did you? Okay.
Like I knew that completely, and then I
Well, now you're wide awake and you're so excited and energetic. Now's a good time to see it. So what we're going to do is we're going to change some things around a little bit. We're going to change this to, I believe you have to change it to radians. Actually, I don't think you do. I think I think if we're working in degrees, we keep it in degrees. Here's the one thing. You see where it says FUNC for function, and then this is parametric. Remember the last thing was parametric equation. This is POL for what? What do you think that is? Polar. There you go. So we changed this to polar. So in order for this to work, you got to change it to polar. Everything else is good. All right. And what we're going to do, if I remember how to do this, I know how to do this on the other calculator. This is the first time I saw it on this one. Let's change this. Use the calculator and change this from polar to rectangular on the calculator. Do you see that blue one right there where it says apps? We're going to hit that. Nope, that's not what I want. I want to hit the second function. So where it says angle, see that behind there, it's hard to read. Hit second function, apps. There we go. It's got all this stuff right here. Like, what in the world's that? Well, look down here. You see this stuff? What do you think the P and then arrow P, or sorry, R and then PR means? Actually, forget the little r. Just say R to P. R to P. What do you think R to P stands for? Very good. Okay, rectangular to polar. But what are we trying to do on this first problem? We're trying to go from polar to rectangular. Do you see anything on here?
Or
yeah, right there. Actually, we can kind of. Now this is still rectangular to polar. See the RP, RP? That's still rectangular to polar. This one right here is what? P to R. Now, let me show you these things. The R, if you're going from rectangular to polar, this right here, this PR, is the resultant in polar form. So this button right here will give you this answer. You follow me? Okay. And then the theta is your angle. So that will give you this. To tell you the truth, it won't give you 161.57. What do you think this answer will give you on the calculator? It's going to give you that 18.43. Okay, and then you have to know better. You have to know what quadrant's in, whether to take it away from 180 and all that kind of stuff. Okay, to be able to get this answer. What do you think this is? Let's scooch out of it. This is P to R. It's the x coordinate, right, of the rectangular form, and this, of course, is the y coordinate. So this number 7 will give you this answer, and the number 8 will give you this answer right here. Does that make sense? Okay. So what we're going to do is we want to find the first part of the answer. So we're going to go. 7, right? So put 7, and I'm going to put this in here. I'm going to put the polar form in here. So I'm going to put, I think this is how you do it, 4, and then there's a comma button right here. It took me forever. It's sitting right in front of me. You know, I'm looking all over this thing. Where's the comma button? I'm looking in the back. I didn't think they put the comma right on the actual button, but it is. Boom, comma, and then 60. Okay, close the parentheses. This should give you the answer, the x answer, right, from polar to rectangular. So we hit enter and cross our fingers. Yay, we got it. All right, so we got a 2. Now, you're going to have to go through that whole routine to get the y. So at least you know that part of it. So then you go through the whole routine. Remember what it was? Second apps. And then we go to what? No, we're still going. I'm sorry, you're right. I'm wrong. We're going to y, right? From polar to rectangular. You could just click 8 if you wanted to, even though you didn't see it on the screen at first, you know. Click 8, and there we go. So now there's polar to the rectangular, the y value. You got to put those numbers in again. 4, 60, and then you hit enter, and there it is, just like we said. Perfect. 4.46. That's kind of nice, isn't it? Just using the calculator instead of going through this. But really, was it really that hard to do this? It probably was less steps punching this into a calculator as it was going through that second apps and then 8 and then putting it in and all that, to tell you the truth. Right? So if you know what's going on, this probably is even less buttons to push and a little bit easier.
I know, like 30 minutes just to explain that easy.
Right. Okay.
He goes through. Remember, you have to hit this button.
Oh, I know.
And then you have to go.
I know he doesn't. He
don't
doesn't
have to do all
expect that you remember anything, does he? I mean, he's thorough. I mean, you can't blame him for it, you know. But he's definitely thorough. But it gets a little old sometimes. I'm like, yeah, you talked about this 100 times. You know, why are you explaining it again? Anyway, here we go. And I probably do the same thing, you know. Well, here we go. Negative 3, 1. We're changing from rectangular, so I go second apps. We're changing it from rectangular to polar. We're going to find the resultant first, right? The magnitude first, so that would be number 5. So I just click 5, and then I put it in here. I put negative 3, 1, and then I hit enter, and there it is, 3.16, just like we said. Isn't that cool? And then we go, 6, right? To find the theta, to find the angle. So I hit 6, then I put negative 3, 1 in again, and then hit that. Oh, it does give you the 161. How about that? Wow, it is nice. I thought they just gave you the 18.43. I guess they knew. Right, they knew since it was the negative 3. Right, so that was cool. All right, and there you go. It's pretty slick, isn't it? I mean, that was pretty quick. That probably was a little faster than doing Pythagorean theorem and doing tangent and all that kind of stuff. But on the problems, I think they say do it without using the rectangular and polar form on the calculator. So there you go. All right, what else we got? I think did that cover it? I think it pretty much did. I mean, I did a couple practice problems on here. Let's do this one. Let's go. Practice A and B are pretty much what I just finished doing. Okay, so I don't think we have to rehash that. You can do those. You can practice those on your own if you want to, just for the sake of time. Practice C was that one with the calculator with the rows looking thing. Remember that? And he goes pretty straightforward. It's in the book. They tell you exactly what to punch in. Right? I'll let you do that too. Practice D and E is what I really want to get to today. So D shouldn't take too long. So let's do practice D. It says, what is equivalent to this? So basically, you want to change this into polar form. To polar form. So this is in rectangular form right now. This is actually the equation of a circle. Remember didn't we graph circles before? Remember we said the radius of the circle would be 3 because it's r squared. Excuse me. So this is in rectangular form. We want to change it to polar form. You're like, how's a circle written in polar form? Well, it is a little bit different. I'll just show you how to do it, okay? Do you remember when we did that stuff when we're solving for x and y in rectangular form? Remember what x was equal to? It was equal to the hypotenuse times the cosine of the angle. Remember that? And what do we call the hypotenuse most of the time? What letter do we give the hypotenuse? R, right, because it means resultant. Remember that? So x would be r times the cosine of the angle. Right? They write this down in the book too. I mean, you could memorize it, but remember, it's the hypotenuse times the cosine of the angle. And so the hypotenuse we use r for resultant, and theta we use for the angle. And y is equal to r times the sine of the angle. Now watch what we're going to do. This is in polar form now. Okay, this is taking a rectangular form situation, the x, right, and changing it to polar form because you got an angle and a magnitude, right? So now this is in polar form. So what am I going to do here? Remember, this was in rectangular form, so instead of writing x in rectangular form, I want to write x in polar form. So what do you think I want to do? Take this r cosine theta and do what to it? Yeah, you're going to square it, right, because you're putting it in for this. You're substituting this in for the x, right? Plugging it in, right? You've heard me say that before, right? And you're right, exactly right. You're eventually going to square it. Then what are you going to do with this? You're going to take this, and where are you going to put that? In for the y, right? You're going to plug that in for the y, and you're going to square that as well. Make sense? Right? And that's all they want you to do. Well, they want you to simplify it, right? And it takes a little bit of work, but that's the basic starting of this. So I'm going to take this thing, put it in for x, which means I'm going to square it. I'll just write the whole thing out here. So we're going to take that whole thing, we're going to square it, and then plus this whole thing, r sine theta, and we're going to square that, and that's equal to 9. Now, how do I square this stuff right here? Well, I square everything in here. I'll take r and I'll square it, and I'll take cosine and I'll square it. This is how we show cosine squared. We put the 2 in between the cosine and the theta. This is going to be r squared times the sine squared, and that's equal to 9. So we squared everything, didn't we? Well, look what they have. They have something in common, don't they? They got an r squared in common. So what do you think I can do if you have something in common like that? Give me a good math word. If I have something in common like that and I want to get it out of there, factor, very good. So I take the r squared and I factor it. What's going to be left if I take out or I factor out of r squared? Cosine squared plus what? Sine squared. That looks familiar, does it? Does it look familiar to you? It simplifies to 1, exactly right. So this whole thing just goes to a 1. 1 times r squared is just r squared, so r squared equals 9. That's not one of our choices, though, because this is multiple choice, okay? They give you choices, and you do have something that looks like this. They just took the 9, slid it over to the left-hand side, set it equal to 0, and that's the choice that they give you for practice problem B. Okay? That wasn't bad, was it? The hardest part was understanding to change it into polar form, right? Making it this, and then you plug stuff in, then you just work it out. Then you make it look like one of the answers that they give you as a choice. Okay? Alright, I know this next one probably bothered you. Remember the one with the, I don't know, what was it? Was it a cannonball or something? Or shooting off at a certain direction? What was it? 4th of July, bottle rocket, that's what it was. Did you try that one at all, or did you watch it on the practice? Take that as a no. Okay. It's alright. I just needed to know where you were on this. So this is practice E. What it says, a bottle rocket, okay, is launched at 60 degrees. So watch what we have here. I'm going to draw the ground. There's the ground right there. Okay? And the bottle rocket is launched at 60 degrees. It's rather steep, isn't it? 60 degrees. So it's launched like this at 60 degrees. And it tells you how fast it was launched. 200 feet per second. I'll just put a 200 there. Just realize that it's feet per second. So what's happening to this thing? Does it just keep going straight up, straight up, straight up and never come down? Of course not. It goes at this angle, but then as soon as it's shot off, it starts on its way down, doesn't it? Even though it's going up for a while. It goes slower and slower up until it eventually actually comes to a stop up here, doesn't it? Vertically, it's still moving horizontally, but vertically it actually comes to a stop, and then it starts coming back down again. So this is what's going on. And the question says, you want to find, what does it say? Let me read it exactly what it says. If the rocket reaches its maximum height after traveling horizontally at 541 feet, where's the maximum height here? That'd be right at the top, wouldn't it? That's the maximum height. And they, the letter that they use is y, because that's the vertical distance. Y represents a vertical distance. So this is the distance. We'll call it y. That's the distance that we want to find. But it says, at that particular point, it traveled horizontally 541 feet. So from here to here was 541 feet. Okay? And we want to find what y actually is. What we're going to do is this. On all these problems, always take, this is in polar form, isn't it? We want to change it into rectangular form. We want to change it into its components, all right? It's a vector. We want to change it to its xy component. Now we can do it pretty easy. Now you're starting to get the hang, hopefully, of changing it to its components. So what's the x going to equal here?
Times the cosine.
Well, I'm sorry. You know what? I kind of lied to you a little bit. Not lied to you, but let me show you something. This is a velocity vector. We will change it in a second, but let me. They throw this in the problem as well. They say that, remember, distance equals rate times time. Remember talking about that the last time? That's what they're doing here. So the distance is represented by the x. X means how far on the x direction, okay? And Vx means the velocity in the x direction. Because this actually has two different velocities. It's got an x direction velocity and it's got a y direction velocity. Okay? So the x is the velocity times the time. And it's just straight like that. But the y at this particular point is a little different. Remember we talked about gravity acting down on it? So we can't just say vyt because it doesn't just go up at a velocity and just keep going, keep going, keep going. It's actually being pushed down on, isn't it? It's being pushed down on by gravity. And so you didn't have to figure this out. They just told it to you, but they said it's negative 16t squared. Remember that? And that has to do with feet per second. In physics, a lot of times you use meters per second, but this is what it would be. This is the acceleration of gravity in feet per second, all right, just so that you know what that's doing. And then we plug that vyt on there. See, this is distance equals rate times time, but then you got to throw this thing in here too because gravity's acting down on it. So that's, you don't have to know how they got that number at this point. If you take a physics class, they'll go through that. But those are the two equations that they give you. So that's important. We're going to use both of those. But what we're going to do here is this. You see this 200 right there? That's your velocity. That's your velocity vector. Okay? What is this Vx? That's the x component of that velocity vector. What's this Vy? That's the y component of that velocity vector. So what am I going to have to do with that velocity vector? I'm going to have to break it down into its x and y component, right? So there's 60 degrees, there's the x component, and there's the y component. And let's just kind of scooch this over so maybe there we go. Okay. So that's the vector right there. That's 200, isn't it? What equals 200? What's this little tiny one right there? That's the Vx. What's this one up and down? That's the what? That's the Vy. Do you see that? That's the y component of the velocity vector. This is the x component of the velocity vector. That's why they label it Vx and Vy. Are you getting this or not? Okay? So I just took that velocity vector. Now, how did you find the Vx? Now we can do that sine and cosine thing. So what was Vx equal to? Let me write that right here. What was the Vx equal to? In this picture right here, how do I find the x? Remember, it's the hypotenuse times the cosine of that angle. And that angle we know, don't we? So it's the hypotenuse, which is what? 200 times the cosine of the angle. And look at that. I can actually get a number for that, can't I? Cosine's a half, and so that's actually going to be 100. I can do that without even a calculator. So that's what Vx is equal to. It's going to help us out a little bit. Let's do the same thing with Vy. Let's find Vy. Well, what's Vy going to be? It's going to be 200 times the sine of the angle, right? And you're going to have to plug that into a calculator, and I already did it. It's 173.21. And that's Vy. So when you have one of these problems, the very first thing you want to do, okay, is this right here. Break it down into its components. You got it? I didn't really do anything here with the blue, did I? That was just given to you in the problem. I just wrote it down, okay? First thing I actually did mathematically was break that velocity vector down into its components, because we're going to use those numbers. That's going to be very, very helpful to us. You with me on that? Okay. So what I want to do is I want to find this y. So I need to plug stuff into this. Well, I know Vy. I can put 173.21 in for that Vy. What's my only problem, though? I don't know something else. Don't know the time. Okay? So what I'm going to do, though, is I'm going to come back to here, and I'm going to find the time. So you're like, well, how am I going to do that? Well, yes. You got some good questions. Look what I know. What do I know in this thing right here? I know Vx, just found it, it's 100. Something else I know. What is it? Look at the information that they gave us. I know what the x is, that's right. This is the x. At this point right here, when I'm trying to find that height, I know what the x is right here, and it's 541. So let's put the stuff in here. 541 equals Vx, which is 100, times what? Times t. Now I can find the time at this particular spot right here. I can find the time from this, right? And so I just divide by 100, and look, I don't even need a calculator for this. Divided by 100 is just 5.41 seconds. And that's what the time is right here, 5.41 seconds. That was pretty helpful to me, because remember what I needed to find? If I'm finding the y right here, remember I knew the Vy, didn't I? The only thing I didn't know was the time. Now I know the time, and I know the Vy. So now I can take both of those things, plug it into this, and I can find my y, and then I'm done. So now it's just a matter of using a calculator. Let me scooch this down so I have a little room to work. Okay? So I'm using this formula right here. Why am I using this formula? Because I'm trying to solve for y. You get it? So y is equal to negative 16 times t squared. Well, I just found the t, 5.41, and I square it. Plus Vy. What's Vy? 173.21. See where all this stuff comes in handy? And then times the t again, which is 5.41. I don't square this one, do I? Because it's not in my formula. Now, you just got to chuck all that in your calculator. And lucky for you, I already did it. And I get 468.75. And that's in feet, because y is a distance, okay? Y is a vertical distance. So it's 468. So this distance right here is 468 what was it, 75? Mm-hmm. Yeah. Feet. Does that make any sense? So let's break it down a little bit, just real quick here, okay? We only got a minute left anyway, so we're done. First thing you did was you broke it down into its components, all right? So you got a Vx and a Vy. And then you got your two equations that they gave you, right? You got to figure out, what did they tell you? What did they actually give you? Well, they gave you the x value, right? Because they said at the top of this height right here, the x was 541. So use this formula right here, stick in both things that you knew, solve for t. You needed t to be able to solve for y. So you put in the t. We already found the Vy. That's the first thing we did. So you stick in the Vy, stick in the t, and you got the y. So really, it wasn't quite as complicated as it first looked. When you look at that big problem, it looks crazy, doesn't it? All those words, all these crazy equations. But just do this, okay? Break it down. So you'll probably have a problem like that, I would think, in that practice, that problem set right there. If you haven't tried it already, I don't know. But that's how you do it. We good? All right. That's it. So take the test this week, and I'll probably give you a couple lessons to work on. Probably 64, 65 is my guess. Right? Let's see how that goes. We're going to do matrices, I think. And I don't know. I haven't seen how he does them, but at first they're pretty easy. At first, it's always pretty easy at first, isn't it?